Number one, we have this big expression with a constant b, and they're wondering which one of our answers represents a factor of the expression. So if I had my function graphed, a factor should intersect the x-axis at one of my x-intercepts of my expression. So of course, I open up Desmos here. I have my expression in there. For the slider b, it's weird. They say they want a positive constant, but notice how it's an x to the fourth. I want to see my 4 roots. So I've tried this on other examples. You drag it until you see your 4 roots and you're done with this function. All I have to do is type in my answer choices and see which one matches our x-intercepts. This one, you can see it's way too high. So I'm going to go ahead and jump down to D here, plus 4b, plus 10. You'll notice it 100% does intersect my two of my x-intercepts from my expression. Jumping back to our problem here, it looks like it's going to be answer choice D. Number 2, we have this r function with a k and an x in it, and they're wondering when we shift r 6 units to the right, which one of these equations down below are going to match. All I have to do, throw my first equation in Desmos, add my slider, and then for my second equation here, I'm just making the subtle changes in my answers to see which one looks like it's shifting right. So I go ahead and I start with answer choice A, plus 6, and that actually moved it to the left. So we know it's not that. I go to B, minus 6, and it does look like it's shifting 6 units to the right. You can always double check with C and D to see, maybe I don't know exactly it's moving 6 to the right, but your other two answers, C and D, completely change your graph. So you know B is going to be the answer here, and just to confirm, yes, it's going to be this one right here. Number 3, little review of exponential functions. We're going to skip the passage for now and just analyze the function in A. We know it's exponential technically for 2 reasons, because they tell us here, but also because we have a variable in our exponent place, right? On top of that, when you know you're dealing with an exponential, this number out front is technically our y-intercept. It's going to be the amount that you're starting with. This number in parentheses here is how it's changing. So always try to imagine if there's like a 1 there, that would mean it's not changing. If it's bigger than 1, that change, say it was like 1.10, that change, that 0.10 is how much you're increasing by, right? 0.10 is the same thing as 10%. In this case, in A, it's 0.82. So that would be a difference, a negative 0.18 or 18%. So in A, we're starting at 1200. We're losing 18% per, and this is where we have to look at our exponent. Our rule for these exponents when they have denominators is it would be really nice if my exponent was 1, right? So what number for t could make our exponent 1? And it's just going to be when t is equal to 12.6. Because 12.6 divided by 12.6 gets me 1. Then I would confirm each, when t is 12.6, my 1200 decreases by 18%. So we really went through A. We'll go through the passage now and try to see what our context is directing us. So up above, they say we have this isotope, exponential, and it is decreasing by 18% every 12.6 minutes. So obviously we got a little bit lucky. How we would go through this one now is I would see when my t is 12.6, like this would get me what, 25.2 or something. This would get me 1. This would also get me that weird, 25.2. All I want to look for, I say we focus on the decreasing by 18% first. Remember, if I'm at 1, it's not changing. So to decrease by 18%, I should see a 0.82. So I'm already looking at A and B because my 1200 is decreasing by 18%, but I want my exponent to be to resolve to 1. So again, in A, when I put 12.6 in for t, I get 1. That means it's going to be 1200 times 0.82. The problem with B is I'm going to have 0.82 raised to the 25.2, and I don't know what that's going to get me. So it's just going to be A here. Number 4, we have an expression, and they're saying the solutions to this quadratic can be written in this form, and we have to solve for k. So I'm already picturing, I throw this in Desmos. It shows me my 2 solutions. There's a special way to type this in where I use my slider for k to get it to line up with one of those solutions. So I jump on Desmos and I have my original function. I prefer to kind of get rid of my equal sign because I like seeing my actual function. And then all we have to do is add a slider for k. And this is great. It tells me, maybe I could just look at my numbers and try to get it to match up, but I'd rather see my slider for k on my graph. So remember, if you're ever trying to match a solution to a function, all you have to do is put an x equals in front of it. And then now it's 100 times easier for me to say, okay, well, to the left, obviously we're getting undefined, but to the right, I just have to really increase this number and just slide it until I can get it to line up with that point. Now, you're not always going to necessarily get it exact like this, so I will usually zoom into like the tens place to make sure. So around the tens place, you can see it is confirmed. I only see one dot between these two. It's going to be k equals 49. You can do this anytime you have expression and then a solution with a slider. Put it x equals so you can get it to line up with your intercepts. That's it. It's going to be k equals 49. Number 5, we have a hollow aluminum pipe in the shape of a right cylinder. The pipe has this outside diameter of 40, a wall thickness of 1, and a height of 120. They want to know the closest volume of the metal wall of this pipe. So what's happening here is we have this kind of empty space that is technically a smaller cylinder. And if I could subtract that from the volume of the entire cylinder as if it was whole, that's going to give me the volume of just that thin wall. So it's just going to be, on our equation sheet, the volume of the cylinder, the bigger cylinder, is going to be pi times the radius of the bigger cylinder. So since the diameter is 40, it's just going to be 20 squared times our height, which is 120. And then what we actually want to do is we want to subtract the volume of the smaller cylinder, the empty space. So that's just going to be pi. And then if the radius of the bigger cylinder is 20, to get the radius of the smaller cylinder, the empty space is just going to be minus the wall thickness, which is minus 1. So that's just going to be 19 squared times 120. So if I calculate the volume of the bigger cylinder, it's going to be 20 squared times pi and times 120. It's like 150,000, and all I have to do is subtract the smaller cylinder. So that's going to be pi times 19 squared and times 120. And I'm getting like 14,700. My answers are pretty disparate, pretty far away from each other, so we know it's just going to be B here. Number 6, we have object P is 240 grams. P is equal to 240. We also have that Q is 2,700% of P. So remember, when you're dealing with percentages, to get them into decimal form to use them in math, you divide by 100. So I get rid of 2 of those zeros. So it's going to be Q is equal to 27. And again, it's of, so it's multiplied, times 240. And that's going to get us, let's see, 27 times 240. So our Q is going to be 6480. And then they tell us P is 20% of R. So P is 240. And I'm going to transcribe it. I'm going to write it exactly how they describe it. It is equals 20% divided by 100, 0.2 of R. So of R. So to solve for R, I just divide both sides by 0.2. So R is going to be 240 divided by 0.2. And we get 1,200. And they're giving us a third piece of information down here. They say the sum of Q and R, so Q plus R, is equal to the product multiplied W and P. So W times P. So all I have to do to solve for my W is divide Q plus R divided by P. So that's just going to be 6,400 plus 1,200, which is 6,480 plus 1,200. That's going to be our 7,680 divided by P, which is 240. And our final answer is 32. Not too bad. That should be our mass of W. Number 7, we have a histogram, a frequency chart that is summarizing NASCAR data. So our x-axis is number of laps, and our frequency is the number of races that had those total number of laps. So to kind of make it easier, instead of a range, I'm just going to go in between. I'm going to say this bar represents the number of races that had 35 laps. This one's 45, this one's 55, and this one's 65. So again, our first column here would represent that we had about 4 races that had 35 total laps. This one maybe is 7 races that had 45 total laps. So all they want to do is they want to add a 51st value, 42 laps. And again, just to make it easy, we'll say 45 laps. So all we would notice on our second data set is it's the same exact data. There would just be one little extra bar here, right? So they want to know what adding this 51st value is how it's going to impact our median and our mean. So what's nice is our data is symmetric, right? We have about 11 values to the left of 55, and we have about 11 values to the right of 55. So remember, your median is just going to be your middle number. When it is so dominantly one number in the middle, right? It looks like we have about 27 55s in the middle. Well, it's going to take 15 or 20 values adding on to a new data set to kind of push us away from 27 being our middle number. One little number to the left, right? If I just wrote out 4 35s, 7 45s, changing it to having 8 45s is not going to change 27 from being your middle number. So right off the bat, saying the median is less or more is just not going to be true. If we had a Roman numeral that the median went unchanged, that would be true. So already anything saying Roman numeral 1 would be wrong. We're liking answer choice D so far. And for our second part, the mean is going to be way more sensitive. What's nice about assuming the mean is we can treat it just like the median. We can assume our mean is going to be 55 here because there's about 11 values to the left, about 11 to the right. Those will, for the most part, cancel each other out. And we can say our mean starts as 55. So what happens when they add a value less than 55, right? They add a 45. All it's going to do is make our mean less. And going through, they say the mean for the new one is going to be less. So Roman numeral 2 is going to be true. Had they introduced a number that was bigger than 55, say it was like 65 laps, that would have made our mean more. So not too bad here. It's going to be B. Number 8. I see a function and they give us the zeros to this function, -4, 2, and 10. And all I have to remember is that my zeros are my solutions. And if they want the value of A, well, I can make my own equation, right? I can say, well, x plus 4, because remember my solutions are what make my function equal 0, my x-intercepts. Also x minus 2. And finally, x minus 10. And all I would have to do is distribute these until I get, my A term, technically my B and my C term as well. So we can do the first one first. That's just going to be x squared minus 2x plus 4x minus 8. Simplified x squared plus 2x minus 8. And then all I have to do is distribute that to x minus 10. That's going to get us x to the third. Plus 2x squared, and then minus 8x, and then my last bit, minus 10x squared. I like to line them up by their powers, so minus 10x squared, minus 20x, and finally plus 80. Technically, all I had to do was my x squared terms anyway, because they want the a value, which is in front of my x squared, so I just add up my x squared terms here, and I'm going to get -8, x to the second. So my a value is my coefficient in front of x squared, so it's just going to be -8 here. Number 8, through Desmos. So it starts similarly. I see zeros to a function, and to make it look more like my function, I want to put my zeros in factored form. So that's just going to be the opposite. It's going to be x plus 4, because -4 would get me 0. That's why it's a 0. X minus 2, and also x minus 10. And all I have to do in Desmos is I have to set this equal to this, and it's going to kind of help me fill in my constants. So if I pull Desmos up here, I already have it typed in. So there's just a few little differences. You just want to change your x with x1. You want to change an equal sign with this symbol in the top left of your keyboard. And then also see right now how my values aren't matching, what we previously got. All I have to do is give like a range for x1. So if x1 is equal to like 1, 2, 3, you can see how it's starting to change. And now you're going to just see the same numbers over and over again. That's when you're done. So yeah, on here, I figured out that a was also equal to -8, and that's going to be our answer. Number 9, I see a circle with a center and a radius, and they give us an expanded form of a circle. And no matter what they want, the a, the b, or the c, if I make my own circle equation with this info, and I expand it, I should be able to solve for all my constants. So remember, for standard form of a circle, it's going to be the opposite of your center for your x. So it's going to be x plus 3 squared. And then it's going to be the opposite of your y because it's in parentheses. So it's going to be y minus 4. And that's because when I plug in -3 or I plug in +4, it gets me to 0. And then finally, your radius is on the other side, and that's always squared. And then all I have to do is expand these and set it equal to my coefficients. So this is just going to get me x squared plus 6x plus 9 plus y squared minus 8y plus 16 is equal to 36. And then what's nice is I only have to worry about my constant here. So I have a plus 9 and a plus 16 on this side. That's going to be plus 25. And they want me to equal 0 on the right side. So I subtract 36. I subtract 36. And my final answer is going to be C is equal to -11. Number 10, right rectangular prism A is similar to right rectangular prism B. The surface area of A is 64. The surface area of B is 1024. And finally, the volume of A is 20. And the volume of B, we don't know. So there's going to be a nice ratio system between any two similar two-dimensional objects or three-dimensional objects. And we'll kind of outline it down below. So we have prisms A and B. And how we're going to compare them is their length ratio, their surface area or area ratio, and their volume ratio. So to kind of give a little example to the left, say these two were cubes and A had a length ratio of 4 times as much, right? So say the lengths of the cube B were 1, 1, and 1. The lengths of A would be 4, 4, and 4. So we'll say our length ratio is 4. Therefore, the surface area ratio is 4 squared because it's the second dimension. And the volume ratio between these two is going to be 4 to the third because it's the third dimension. So that's literally it. What they're going to do in these types of problems is they're going to give you one or kind of like parts of multiple ratios. So we'll start with our surface area ratio in this one. We have surface area of A is 64. The surface area of B is 1024. So all I have to do is get this ratio and I'll get 16. So before I jump to volume, I have to go backwards to my length ratio first. And remember that my surface area ratio is my length ratio squared. So my length ratio is actually 4 because 4 squared is 16. And then my volume ratio is going to be 4 to the third, which is 64. Now they had to have given us, one of the remaining two here. They do. They give us the volume of A, which is 20. So all I have to do is do 20 times the 64, and that's going to get me 1280 for the volume of B. And that's it. Number 11. An ecologist monitored two populations of frogs, a hunter frog and a forager frog. At the start of this observation period, there were equal numbers of the two, so there's probably going to be a change. The easiest number to start with for both populations is always going to be 100. And then let's see what happens over this period. So we have, by the end of the week, the number of forager frogs had increased by 1200%. So this is going to be a percentage trick they love to do. There's going to be 3 main types of percent changes. There's going to be of, versus, more than, and increased by. So if it was 1200% of, that would mean you take your forager frogs and you times by 12, right? The reason why you times by 12 is because your percentages, you always divide by 100 before you do math with them. So that would turn this into times 12. But if it's ever increased by or more than, you add 1. So instead of multiplying by 12 here, you would multiply by 13 because it's increased by. So forager frogs actually turns into 1300 total. And then let's see how the hunter frogs change. The hunter frogs increased by 400%, divide by 100. So that just turns into 4. And again, since if it was of, it would be times 4. If it's increased by or 400% more than, it's going to be times 5. So we actually end up with 500 hunter frogs. And then finally, they want us to they say that hunter frogs are p% less than the number of forager frogs. So first we get the numerical amount that's less, and that's going to be 1300 minus 500. So there's an 800 difference. And then you always divide by your total, the forager frogs. So if I divide 800 over 1300, I should get 0.6154 or 61.54% for how much the hunter frogs are less than forager frogs. Number 12, the area of a rectangular field is increasing at a rate of 120 square feet per hour. Which of the following is closest to the rate in square meters per minute? So this is a classic rate change problem. Down below, we'll start with our initial rate of 120 feet squared per 1 hour. And I like to organize it in a certain way, which will kind of make sense as we go. So again, our goal is to change the feet squared and the hours into their appropriate units. We can start with feet. So our first ratio is every 3.3 feet should get us to meters. So in 3.3 feet, we get 1 meter. And we're actually going to write this twice because we start with feet squared. So what ends up happening, how we kind of read this chart, is it's like one big fraction. And then we multiply everything up top, and we end up multiplying everything below, and then we divide. So what I just did is feet squared is going to cancel out with feet times feet. And now my numerator units are meters times meters, which is going to be square meters. And then I just have to finish with converting hours into minutes. So in 1 hour, there's going to be 60 minutes. And same thing, we cross out 1 hour with 1 hour because they're dividing. So now I see meters times meters, which is square meters, divided by minutes, which is exactly what we wanted. So all I have to do now is 120. It's just ones across the top. So I'm going to divide by 3.3 times 3.3 times 60. And I should get a 0.18.